Hello everyone. In this video we will discuss about the molecular orbital theory. Now in terms of the chemical bonding theories, right, we have started with the Lewis theory, which explains mostly how the atoms are bonded in a given molecule. Then we have seen the valence shell electron pair repulsion theory, which we call in short as the VSEPR theory. So VSEPR theory addresses the idea of shapes of molecules and the bond angles. Both these theories, right, they are based on the conventional understanding of the atom, which means we'll consider the atom to be having a nucleus around which the electrons, particles will be revolving. Whereas the valence bond theory and the current theory, molecular orbital theory, right, both of them are based on the quantum model of the atom. So what do you mean by the quantum model of the atom? It basically considers that the electron to be in the form of an wave. Valence bond theory already we have discussed about it in the previous videos, so we'll be able to understand about again the concept of shapes of molecules. Already we have seen the shapes of molecules in the VSEPR theory also, but valence bond theory not only gives the idea of shapes of molecules but also gives explanation to why different bonds are having different energies, the concept of bond enthalpy, bond length and other parameters also. The VB theory will explain using the concept of the overlapping of atomic orbitals. Okay, and also we have the hybridization phenomena in the valence bond theory. But some properties of these substances, including the magnetic properties of molecules like O2. So most of these theories, right, they predict that the diatomic oxygen O2 molecule will have no unpaired electrons, and hence it will be having a diamagnetic nature. That is what is predicted based upon most of these chemical bonding theories. But in reality O2 will be paramagnetic, so which suggests that this must be having some unpaired electrons. So none of the theories they were able to explain this paramagnetic nature of O2. Also some of the ideas like bond order being a fractional value. So normally when we say bond order 1 means what? It is a single bond. Bond order 2 means double bond. 3 means triple bond. But if you have bond order 1.5 or bond order 2.5, so this could not be explained comprehensively in terms of what it actually translates into. So all these things the molecular orbital theory will be able to provide better explanation. Okay, and from the very word, right, molecular orbital theory, so here we are going to talk about the concept of molecular orbitals. So before we go into the molecular orbitals, right, let us just quickly rewind our understanding of the atomic orbitals. Now Schrödinger wave equation basically gives the equation for the amplitude of the electron wave. This is what we will indicate with the symbol psi, correct? So the s orbitals will be having a spherical symmetric distribution, p orbitals will have a dumbbell shaped, d will have a double dumbbell shape, f will have even more diffused. So basically Schrödinger wave equation will help us to understand what is the distribution of this electron wave around the nucleus. And the thing is, when we talk about the atomic orbitals, right, this wave function will be influenced by the nucleus of the atom. So that is how the Schrödinger wave equations will be written. So the wave equation will be influenced by the nucleus of the atom. Whichever atom we are writing the atomic orbital equations, the wave equation will be influenced by that nucleus. So this is the concept of atomic orbital, and we have seen when we are trying to fill electrons into atomic orbitals, we will follow the rules of Bohr principle, which is we'll start filling lower energy level first and then go to the higher energy level. And also we have Pauli's exclusion principle, based on which the maximum capacity of electrons is what? 2 in any orbital. And we have Hund's rule of maximum multiplicity. What is it? When we are filling electrons into degenerate orbitals, first we will fill one with parallel spin, then we'll start pairing them up. Okay, so all these things we have talked about in the atomic orbitals. Now let us talk about the concept of molecular orbital. So just like the way in an atom, right, if you have an atom, say for example there is an atom A, the electrons of the atom A, right, will be filled where? They will be filled into the atomic orbitals. Similarly, if you are thinking about a molecule, let us say we talk about a molecule formed between A and B. The electrons of this molecule, electrons means not just the valence electrons, we are talking about all the electrons. The electrons in a molecule will be present in the molecular orbitals, just like the electrons in an atom are present in where? Atomic orbitals. So every molecule, right now we will start looking at the molecular orbitals. The thing is, when we have an electron in atomic orbital, right, even as per the Schrodinger wave equation, we will see that the electron will be influenced only by that particular nucleus, whichever atom the electron belongs to. But in a molecular orbital, the electrons will be influenced by two atoms if it is a diatomic molecule. If we have a triatomic molecule, imagine we have three atoms. The electrons will be influenced by all the three nuclei, like that. So depending upon whatever is the number of atoms in that molecule, all of them will be able to influence the molecular, the electrons in that particular molecule. So what we can say is the atomic orbitals are monocentric, means they have one center, which is the nucleus of the respective atom. Okay, so they will be what? Monocentric. Whereas the molecular orbitals will be polycentric, means like, if you think about diatomic molecule, we have how many nuclei influencing the electrons? 2. Triatomic means 3, like that. Okay. Now when we talk about the wave equation, the electron probability distribution, right, the function around a nucleus in an atom is given by the atomic orbital. So atomic orbital wave function will be giving us what? How the electron wave is distributed. Similarly, the electron probability distribution around a group of nuclei, means we are talking about the electrons inside the molecule. These equations are given by what? The molecular orbital. Just like the way we give the equations for the atomic orbital, we will also give the equations for the molecular orbital. Okay. Now we will see how we will get these equations. That is a task. Okay, how we will get the equations, we have to see. Already the atomic orbitals, right, Schrodinger has done work in terms of getting the equations for the atomic orbitals. Okay. Now when we have these molecular orbitals, we have to now fill the electrons into molecular orbitals. So in atomic orbitals, when you are filling electrons, right, we will follow the Abbo principle, Pauli's exclusion principle, and the Hund's rule. Similarly, when we are filling up electrons into the molecular orbitals, we will again follow the same principles. We will follow the Abbo principle, we will follow the Pauli's exclusion rule, also we will follow the Hund's rule of maximum multiplicity. We will go and look at these examples as to how we will fill the molecular orbitals. But let us focus on what is the first task. What is the first task? How do we get these molecular orbitals? We know, okay, we can have molecular orbitals where the electron is going to be now influenced by all the nuclei inside that particular molecule. The understanding for this comes from the fact that, let's say for example, you have nucleus 1, nucleus 2. Normally what we think is if there is an electron that is revolving around nucleus 1, we'll assume that this is influenced only by the nucleus 1. But when they are in such a close proximity, nucleus 2 also will influence the electron. The electron of that atom 1 will be influenced by the nucleus 2 also. And this is the basic idea of the molecular orbital. So we can not take out the influence of the nucleus 2 on electrons of atom 1. Similarly, electrons of atom 2, right, they will also be influenced by the nucleus of atom 1. So all the electrons of the molecule, so it is not just about the valence electrons, that is another thing that we need to keep in mind. All electrons of the molecules will be what we will be considering in terms of our molecular orbital discussion. So it is not just about the valence electrons, it is about the all electrons. Okay. Now what we will do is we will try to see how we will get the molecular orbitals. Now again, if we have to go and write down the equations of these electron waves by considering the influence of nucleus 1 and nucleus 2, we have to again redo whatever Schrodinger has done. And obviously, I'm sure you are able to recall the equation of Schrodinger wave equation, right? That itself will look complicated. So we definitely will not be able to go and again redo all these equations. But what we have in our syllabus is a very simplistic approach. That approach is what we call as the linear combination of atomic orbitals, in short LCAO approach. So we will be able to understand the molecular orbitals by using this LCAO approach. So we'll see what is this linear combination of atomic orbitals approach. Now the linear combination of atomic orbitals approach basically is a simple idea that if you have atomic orbital 1 and atomic orbital 2, let's say, when these two combine, they will be giving rise to molecular orbitals. When these two combine, they will be giving rise to what? The molecular orbitals. This is what is the simple concept of linear combination. Now how the linear combination occurs? If say for example we look at atomic orbitals that have to undergo the combination to form molecular orbitals. These atomic orbitals should first be having comparable energies. Means what? We cannot add or we cannot combine a 1s orbital to 7s orbital, because they will definitely have different energy levels. So the atomic orbital should have what? Comparable energies, and also they should have proper symmetry. They should be having what? Proper symmetry. So when we are looking at combining atomic orbitals to produce a molecular orbital, we should consider atomic orbitals that have comparable energies and that will have proper symmetry for the combination to happen. And the combination, right, will be giving us same number of molecular orbitals as that of the atomic orbitals. Means the number of molecular orbitals formed, right, will be equal to the number of combining atomic orbitals. Say for example, we are combining two atomic orbitals. We are going to get exactly two molecular orbitals. And one of these molecular orbitals will be called as the bonding molecular orbital, which will have less energy and hence it will be what? More stable. Other will be called as anti-bonding molecular orbital. So when we combine two simple atomic orbitals, we will get two molecular orbitals. One will be less energy, we call it as what? Bonding molecular orbital. Other will be more energy, we will call it as what? Anti-bonding molecular orbital. Now as we see, the bonding molecular orbital will have less energy and that will be giving us what? More stability than the anti-bonding molecular orbital. So anti-bonding will have high energy and less stability. So this is how we will get the molecular orbital. Now we will look at it with an example so that we will be able to understand. Okay, so if you want to look at how we can get the molecular orbitals, take a look at this. You have imagine two wave equations. Okay, so here to make it easy, we have taken the normal representation of wave. It is not like electron wave is going to look like this. We have taken simple wave so that we can understand this better. So you see, this is the first wave equation, second equation. When wave will have what? Crust and trough, right? So when the two waves are adding each other, you see what happens? You have a bump and another bump. When they add, what is going to happen? You will get a bigger bump. Means this is what we call as the constructive interference. You will learn about it in physics, waves and oscillation chapter, right? You will be able to learn more of how the constructive interference happens and all these things. But here just very simple understanding for us. If you think of the two waves like this, when both the upward crusts are adding, we will call it as what? Constructive. Here trough will be adding like that. So this is what we call as a constructive interference. So we can think of it like what? Equation of the first wave adding to equation of second wave. That is going to give us the equation for the bonding molecular orbital. So bonding molecular orbital, how do we get it? We will simply get it by the addition. Like we will represent it like this, bonding. So bonding will be what? It will be given by what? The equation for the atomic orbital A plus equation for the atomic orbital B. That is what is going to give us the bonding molecular orbital. If you have the wave equation of A and wave equation of B, you can see here what is happening. Over here what is happening? The crust is matching with the trough. So when you add both of them, it is like subtraction, isn't it? They will subtract. So this is what we call as the destructive interference. What do we call it as? Destructive interference. Okay. So when you have destructive interference, we will be getting anti-bonding molecular orbital. So the anti-bonding molecular orbital will indicate this with the subscript A. It will be equal to what? Wave equation of atomic orbital of A minus wave equation of atomic orbital of B. This is how we are going to get the anti-bonding molecular orbital equation. So this is what we call as the linear combination of atomic orbitals. So this is the simplistic approach to understand how the molecular orbitals will be formed. So the other thing is, we said bonding will have less energy, anti-bonding will have more energy. But when you add up energies, of the bonding orbital and anti-bonding orbital. That's what we are getting after the combination. What is there before the combination? Before the combination we have atomic orbital of A and atomic orbital of B. The energy is right. Initially whatever is the total energy, which is energy of the atomic orbital A plus energy of the atomic orbital B, that will be equal to what? That will be equal to energy of the bonding orbital plus energy of the anti-bonding orbital. So basically no energy will be lost or gained. Now we will look at how the combination can happen with specific cases. If you have 1s orbital of an atom, okay, so let's say atom A, 1s of atom B, when they both combine we will get 2 molecular orbital. So here the combination, right, like if you see this is the nuclear axis, right, how they will combine? They will combine head to head. Remember in the valence bond theory, right, what do we call this kind of an overlap? We will call it as sigma, head to head overlap, correct? So here we will follow the same notation. So we will get the molecular orbitals, right? The bonding we will call it as sigma 1s, anti-bonding we will call it as what? Sigma star 1s. So we can see sigma 1s will have a lower energy, sigma star 1s will have a higher energy, okay? And one more thing is, if you see around the nucleus, right, there will be symmetry. In case of the sigma you will see complete symmetry is there around the nucleus. But here around the nucleus, right, the anti-bonding orbital, there will be no symmetry. Around the nucleus there will be no symmetry, okay? So you will see that symmetry will be happening in which case? In the case of the sigma bonding orbitals, we will see that there will be what? There will be a symmetry of the electron cloud around the nucleus. But anti-bonding there will be no symmetry, okay? Now we will move on to the next one. If you take the z axis to be the internuclear axis, generally that is what we consider. You see a 2pz of one atom and 2pz of another atom. Remember the concept? The atomic orbitals of comparable energy and symmetry, they only will be able to combine to give us the molecular orbitals. So 2pz and 2pz, when they have the constructive interference, we can see they are adding, plus plus they will be adding. So we will get what? Sigma 2pz. Why are we using the word sigma? Because it is what? Head to head overlap. And when the destructive interference happens, means subtraction, you can see. So what we are going to get is an anti-bonding molecular orbital. So we will call it as what? Sigma star 2pz. Okay. Now if we have the symmetry concept, look at the symmetry concept. Here we will see there is a symmetry. Around the nucleus we will have a symmetry. But here there will be no symmetry. One side you have a minus, other side you have plus. Means what? The sigma bonding orbitals, right, they will be what? Symmetric. They will be symmetric around the nucleus, okay? But the point is what? Between these two, which will have lower energy? Sigma 2p z will have a lower energy than sigma star. So always the bonding will have a lesser energy than the anti-bonding, okay? Now when it comes to the sidewise overlap, if you take the z axis as the internuclear axis, the 2px, when they have to combine, how they will combine? They will have to combine sideways. Look at it. If you have plus plus adding, minus minus adding, what we are going to get? We will be getting the pi 2px. Similarly we will also have what? Pi 2py. Okay. Now here when they undergo destructive interference, that is going to give us pi star 2px. In case of y 2py orbitals, it will be what? Pi star 2py. The shapes will look identical, okay? So here you will see one interesting thing. You know what? About the nucleus, if you position the nucleus, right, the pi 2px is asymmetric. You can see one side you have a plus, one side you have a minus. Whereas pi star will be symmetric. You see this side minus means exactly opposite is minus. Plus means exactly opposite is plus. Which means what? The pi star 2px and pi star 2py, they will be symmetrical. Okay. So just to look at what are we essentially talking about. If you have the 1s of atom A and 1s orbital of atom B, they both overlap. What we are going to get? Sigma 1s and sigma star 1s. Okay. If the 2s of atom A and 2s of atom B, they will overlap. What we are going to get? Sigma 2s, sigma star 2s. Always the S orbitals will be giving us what? Only the head to head overlap. So we'll have what? Sigma. If we have 2pz, we'll get what? Sigma 2pz and sigma star 2pz. Then 2px and 2py cases, what we are going to get? Pi 2px, pi 2py. These are the bonding. Pi star 2px and pi star 2py are what? They are the anti-bonding. So this is how we are going to get the molecular orbitals. Okay. Now the thing is, we will have to understand how these molecular orbitals will be arranged in terms of their energy level. Okay, so because only when we know the energy level arrangement, we will be able to talk about the electronic configuration. So here also same word, we'll use what? Electronic configuration for the molecules. But before we go into the discussion about the electronic configuration, right, we will just conclude one symmetry point. That is, if you have seen, right, we have talked about it, sigma 1s, sigma 2pz and pi star 2px and pi star 2py. All of them are what? They have symmetry about the nucleus. So if a molecular orbital has symmetry with respect to the center of the nucleus, it is called as what? Gerard. If it is not, it will be called as what? Ungerard. So we can see what will be the Gerard ones. What will be Gerard ones? The sigma bonding and pi star, which is the anti-bonding. Pi star 2px and pi star 2py. What will be the ungerard or asymmetric ones? It will be what? The pi bonding, which is pi 2px and pi 2py, and the sigma star anti-bonding, which is what? Sigma star 1s as well as sigma star 2pz. They are what? Ungerard. So they are asymmetric. So these are what? Symmetric about the nucleus, and these are what? Asymmetric. Okay, so this is what we have in terms of the symmetric and asymmetric nature of the molecular orbitals. Okay, now we'll go and look at what is the energy level arrangement of these molecular orbitals. Okay, so in terms of the energy level arrangement, this is more of an memory based scheme, and we do get, like, any question on the molecular orbital theory, right, can be answered only when we are able to remember this particular energy level. You'll see that, even if you take a look at the previous year questions in competitive examinations, you will see that they can be answered only when we remember this molecular orbital energy level diagram. So here the thing is, we have a change in the order up to 14 electrons, and as I think probably we have said, our syllabus purview, right, is only considering what? Diatomic molecules or ions. That is what we will be covering in terms of the study of molecular orbital theory. Okay, that is what is there in our syllabus. So if you look at the molecules like B2, C2, N2 up to 14 electrons, this is important. Up to what? 14 electrons. What is the order? Sigma 1s less than sigma star 1s, sigma 2s less than sigma star 2s. Then pi 2px and pi 2py, they will be degenerate. You can see they have same energy. Then sigma 2pz. Then comes pi star 2px and pi star 2py. Then will be the sigma star 2pz. This is the order for up to the molecules having 14 electrons. Molecules or ions having 14 electrons. But if you have more than 14 electrons, means 15, 16 like that, okay, then the order will be different. You know where the difference is going to come? The difference is going to come just in the case of the sigma 2pz and the pi 2px and pi 2py. Okay, so you see what is going to happen after 14 or more than 14 electrons, right? What is the order we have? The sigma 2pz will have a lesser energy than pi 2px and pi 2py. That is the only difference. Other things will be as it is. Look at it. Sigma 1s, sigma star 1s, sigma 2s, sigma star 2s. Then the difference will come. So here sigma 2pz will have a lesser energy than pi 2px and pi 2py. Then pi star 2px and pi star 2py will be as it is at least the way we consider, right? Sigma star 2pz will be having a higher energy. Okay, that is going to be at that, the highest energy level. So why are we only looking at up to the sigma star 2pz? Why not after that? Because the molecules that we will be considering, right, generally in our syllabus we will consider up to the F2 molecule, which means what? Each fluorine has got 9 electrons, so 9 plus 9 is what? 18 electrons. Okay, so if you look at 18 electrons means we can see each of these orbitals, right? What is the capacity? 2. So 2 plus 2 plus 2 plus 2, we'll have to, so here 2 orbitals are there, 4. Here 2 orbitals are there, 4. So add them, this is what? 10 and another 10, 20. So we will not be able to go beyond this, the molecules or the ions that we will generally be studying. Okay, that is the reason why we will try to limit the energy level diagram up to what? Sigma star 2pz. But if you want to look at it means we will be able to look at even after this also, after sigma star 2pz also we will be able to look at the energy level diagram, but this is sufficient for us. So here what is the most important thing? The difference in the energy order between the up to 14 category and then after 14 or more than 14. Up to 14 means what? Sigma 1s, sigma star 1s, sigma 2s, sigma star 2s, then pi 2px and pi 2p will be degenerate, then sigma 2pz will come, then pi star 2px and pi star 2py, then sigma star 2pz. Always sigma star 2pz is the peak. Okay, so these two will not be changed after 14. What is the only difference? The sigma 2pz will have a lesser energy than pi 2px and pi 2py. That is the only difference. Okay, so this is what is the energy level diagram of the molecular orbitals. Now what we'll do is we'll try to look at the molecular electronic arrangement of O2. O2 means what? Diatomic oxygen. What is the number of electrons in this? It has got totally each oxygen atom. So remember, here we are not talking about the valence electrons, we are talking about the total electrons of oxygens. Each oxygen has got 8 electrons, right? So 8 plus 8 is what? 8 plus 8 is what? 16 electrons. So that is the total number of electrons we have. Now look at the order for more than 14 electrons, right? Because this is 16. What is the order? Sigma 1s, sigma star 1s, sigma 2s, sigma star 2s, sigma 2pz, then pi 2px will be equal to pi 2py, degenerate, pi star 2px, pi star 2py, degenerate, then sigma star 2pz. Now what is it? This is the energy level diagram. This is as per the Aubu principle. Now when we are filling up electrons, what we have to do? We have to fill each of the lower energy level completely, then go to the higher energy level. That is one. Other thing is what? Each orbital maximum capacity is 2 electrons. What is it? Pauli's exclusion principle. Then when we are filling up electrons into the degenerate orbitals, first we have to fill them with parallel spin, then we will start pairing them. So look at it. Sigma 1s, right? Orbital 2 electrons will take. Sigma star 1s 2 electrons will take. Sigma 2s 2 electrons. Sigma star, sigma 2pz. How many are over? 10 are over. How many more are remaining? 6 are remaining, right? Totally 16 we have. So imagine we'll give a 1 here, another 1. Then we'll start pairing them. Both of them will get 2 electrons each. So totally 4. After filling these degenerate completely, we filled. Then we are having how many electrons? 2 more electrons are left. Here also degenerate, right? Means we have to give 1 electron here, 1 electron here. So what is the arrangement? Sigma 1s 2 electrons, sigma star 1s 2 electrons, sigma 2s 2 electrons, sigma star 2s 2 electrons, sigma 2pz 2 electrons, pi 2px 2 electrons, pi 2py 2 electrons, pi star 2px 1 electron, pi star 2py 1 electron. Okay, so what is it? We can see the arrangement, right? By the way, in some textbooks, right, you will see that instead of mentioning this sigma 1s 2 electrons and sigma star 1s 2 electrons, right, they will indicate this kk. So this basically means what? You are indicating that sigma 1s 2 electrons and sigma star 1s 2 electrons. The same arrangement, how we can write it? Instead of saying sigma 1s, instead of saying sigma 1s 2 electrons and sigma star 1s 2 electrons, what we can say? We can say kk. That represents what? The arrangement of sigma 1s 2 electrons and sigma star 1s 2 electrons. Okay, so you can see sigma 2s 2 electrons, sigma star 2s 2 electrons, sigma 2pz 2 electrons, pi 2px 2 electrons, pi 2py 2 electrons, degenerate. Then pi star 2px is 1 electron, pi star 2py is what? 1 electron. So this is the electronic arrangement of O2. Now I'll just give you one quick insight into how the molecular orbital theory will be able to explain the paramagnetic nature of oxygen. So you see here the arrangement of electrons into the molecular orbitals, right? Are you able to see unpaired electrons? Yes or not? We are able to see the unpaired electrons, right? Where are they? The sigma star 2px and sigma star 2py, they are having unpaired electrons, and that is going to be the reason. We'll discuss about it later, but just insight into how the molecular orbital theory will be able to explain the paramagnetic nature of diatomic oxygen molecule. So we can look at one more example, the electronic configuration of nitrogen molecule. So here when we say electronic configuration, we are talking about what? The molecular electronic configuration. So what is it? This is what? Nitrogen means we have each nitrogen is having what? 7 electrons, total electrons, not just the valence. 7 plus 7 is what? 14. So here we look at what is the order up to 14 electrons. What is the order up to 14 electrons? Sigma 1s, sigma star 1s, sigma 2s, sigma star 2s, then pi 2px and pi 2py degenerate will be having a lower energy than the sigma 2pz. Then of course the pi star 2px and pi star 2py degenerate level, then sigma star 2pz. Here look at it, 14 we have, right? 2 will give here, 2 will give here, 2 will give here, 2 will give here. Totally how many are over? 8 are over. So from 14 you will take out 8, means we will have 6, right? So we can give 1 here, 1, and then we can pair both of them. So totally how many are over? 4 are over. We will be having still 2 more electrons. Where we will give the 2 electrons? Sigma 2pz, we will give the 2 electrons. Okay. So this is about the electronic arrangement of the N2. So we can see what is it? Sigma 1s will have 2 electrons, sigma star 1s will have 2 electrons, sigma 2s will have 2 electrons, sigma star 2s will have 2 electrons, pi 2px will have 2 electrons, pi 2py also will have 2 electrons. Then sigma 2pz also will have 2 electrons. That is the electronic arrangement of the diatomic nitrogen molecule. So this is how we are going to look at the electronic arrangement of the molecules based on the molecular orbital theory. Okay. Now in the next continuation video for the molecular orbital theory, we will be able to see how the molecular orbital theory will be able to explain some of the phenomena that the other theories were not able to provide comprehensive explanation for. Okay. We'll see in the next video.